Okay, so in this lecture, I'll try to cover a bit of convex geometry that's dealing with this idea of convex bodies and how to approximate them using ellipsoids. So this is a very core technique in a lot of algorithms in computer science, and we will see how this can be used then in the area called optimal design, which is a very rich area in statistics where the goal is to find a good set of points in a given set of points such that we can use those that small number of points to get a good approximation for the whole set. So we'll see these two things. One is this theorem called John's theorem, a very famous theorem that characterizes how an ellipsoid in high dimensions looks uh, when it is contained inside a convex body and has maximum volume. And on the other side, we'll see the idea of optimal design. So in this first part, I'll cover some basic definitions, and then we will move on to uh, John's theorem, and then in the next third part, we'll see optimal design. So let me start with some basic preliminaries. So we'll start with so in this series of lectures, I'll always stick to the space R power n, which is the space of n-dimensional real vectors. This is also called the n-dimensional Euclidean space. And here we will use the Euclidean norm, which is denoted as norm x, which is defined as summation I equals to 1 to n xi square, where x is basically a member of R power n and x is the coordinates x1, x2 up to xn. So this basic notion of the Euclidean norm is what we will use throughout, and this will also this norm can also be used to define distances between 2 points, which we will state as x minus y. Norm of this is also called the Euclidean distance, which is nothing but right. And you can see that this is actually a metric in the Euclidean space because it's symmetric, it's zero at zero, and uh, it's like the it's zero between same points, it's symmetric, and it satisfies the triangle inequality. So we'll not go into that proof, but this is a metric on the Euclidean space, which is the corresponding metric to the Euclidean norm. And throughout our discussion, we will extensively use these uh, definitions. And so we'll start with some nice sets in this Rn space, which we will use multiple times throughout our uh, discussion. So I'll start. First is the idea of unit balls. So we'll call this uh, only ball, and it will mean only unit ball. We'll denote this with the uh, b subscript n, and this is the collection of all vectors whose norm is less than equals to 1. So basically this is the analog of a circle in 2D, unit circle in 2D, or a sphere in 3D. um, right? And in high dimensions, this is given by norm of x less than equals to 1. Then we have the unit sphere. We will call this just sphere. and this will denote with S super n minus 1. This is given as the collection of all vectors in Rn such that their norm is exactly equals to 1. Note that we denote it with Sn minus 1 because the fact is that this equality constraints, so it constrains the degrees of freedom. So once you fix n minus 1 coordinates of x, you automatically get the other coordinate to come out to a specific value. But in the case of a ball, you can actually set all the coordinates of x sort of independently as long as their their norm is less than equals to 1. So that's why we use this notation as n minus 1, and instead for the ball we use bn. Yeah. Then we have this definition called a hyperplane. So this hyperplane is a fundamental object in the study of convex geometry, and we'll see how this is so fundamental. But first, let me give you the definition of a hyperplane. A hyperplane is basically the generalization of a line in 2D or a plane surface in 3D. So we will define a hyperplane with the use of two objects, which is a vector in Rn and a real, right? So given these two things, we define hyperplane as H. This is the set of all vectors such that x inner product phi is equals to t, right? So this inner product is again offshoot of the definition of the Euclidean norm. So think of this inner product as basically the inner product is defined as x comma y is equals summation I equals to 1 to n xi yi, right? This is the dot product or a scalar product that we have seen in our say basic physics course or math courses. And the relation between this inner product and the norm is that is for the vector x, the inner product of x with itself is actually the square of the Euclidean norm. So basically this inner product, the distance metric, and the Euclidean norm, these three things are in some sense very interrelated, and they are kind of, yeah, generating from the same definition in some sense. Anyway, so this is a hyperplane. Hyperplane is basically this all vectors such that the inner product of x with phi is exactly equals to t. So you can see that on 2D, this basically means that if I give you a v which is nothing but say v1, v2, and we restrict it in 2D, and then what you have is basically v1 x1 plus v2 x2 is equals to t, and if you draw it in a 2D graph and say this is your x1 coordinate, this is your x2 coordinate, then this is, you can see that this is an equation of a straight line, right? Somewhat like this. So in high dimensions, we call this hyperplane. In low dimension, in 2D, it's a straight line, and in 3 dimension, it's a plane, right? So also note that this hyperplane also has 1 degree of freedom less than the dimension of the ambient space. And this is again because of the fact that once you fix, say in 2D, for example, if you fix x1, then x2 is automatically fixed, right? So this is again uh, n minus 1 dimensional object lying in Rn. So given this definition, we also for a hyperplane we can define this objects called half spaces. So what is a half space? Half space is basically one side of a hyperplane. So formally we will define this as, again, we are given V in Rn and T in R. Then there are two half spaces that we can define, and we will denote with H plus, in some sense the positive half space, which is defined as all vectors in Rn such that our X inner product phi is greater than or equals T, and we'll denote with H minus the other half space, which is basically X belongs to Rn, X inner product phi is less than equals to T, right? So how does this look in, for example, 2D? In 2D, like let's again look at a line. So we know that hyperplane is a line. So X inner product phi equals to T. If we draw it out in 2D, so this is the line, right? And then what does it mean for X inner product phi to be greater than equals T? So say T is positive for us, okay? Let's imagine T is greater than 0. So then you can see that if you put X equals to 0 in this equation, X inner product phi, then you get X. So 0 inner product phi is actually 0, and therefore you have that this is less than T. So 0 lies in the H minus space, right? So basically, I mean, in some sense, you can imagine that this part is our H minus. So all points which are in this side of the line is H minus, and points which are on this blue side of the line are actually H plus. So this is our H plus and this is our H minus, right? So these are some basic definitions and we will extensively use them. And now let me move on to defining convexity, because as I said, like we will deal with convex geometry. So I'll first define, like recap convexity, and then I'll define a convex body. So let me start convexity. So what is a convex set? I think most of us can recall that a convex set S. So S is a convex set. This basically means that if X and Y both belongs to S, then a convex combination, which is given by this, also belongs to S for all lambda in 0, 1. So this form, right, lambda x plus 1 minus lambda y, this is called a convex combination when lambda lies between 0 and 1, both inclusive. So this says that a convex set is such a set, right, that if you take 2 points from that set, then the convex combination of these 2 points, any convex combination of these 2 points, will lie inside that set. So basically, you can think of this convex combination as telling you that, so this is your set S, right? And you pick 2 points, X here and Y here. Then this convex combination in some way is basically the line that connects these 2 points. And therefore, we require that this whole line segment lies inside X. So, for example, if I have something like, oops, something like this, right? And if I pick 2 points x here and y here, then what happens to the line connecting them, right? The line segment now goes outside the set. So this segment is outside the set S. So this is not a convex set. So call this set T. Then we have S is convex, T is not convex, right? So yeah, and moreover, like, so you can see that, like, I mean, the object that we defined earlier, right? From this, you can see that the unit ball, right, is a convex set. Why? I mean, it's an easy exercise to show that if x is in the ball, that a norm of x is less than equals to 1 and norm of y is less than equals to 1, then lambda x plus 1 minus lambda y also has a norm less than equals to 1. And you can show this by using the triangle inequality. So this is indeed a convex set. But the sphere, on the other hand, is not a convex set. Because why? The sphere is basically the surface of the ball, right? So if you can imagine that if you have in 2D, for example, a circle, and you pick 2 points on the circle, and by circle I mean only the circumference of the object, right? Not the interior, the inside part of the circle, only the perimeter or the circumference of the circle. And if you take 2 points on this and connect them with a straight line, then you will see that the segment lies outside this circumference, right? So the sphere is, in that sense, not a convex body, like a convex set. Again, you can show that the hyperplane is indeed a convex set. In fact, these half spaces are also convex sets. So yeah. Next, we have this concept called. So if you don't have a, so I give you a set, and the set is not convex, right? Then can you include some more points in the set and make this set convex somehow? So this is called the convex hull of a set. So convex hull of a set S. This is basically the smallest convex set that contains S, right? So smallest convex set that contains S. And how do we formally define this? It's basically, we'll use this notation of conv of S. This is intersection of all A convex. So all convex sets, right, such that A contains S. So you can see that this is an intersection of many convex sets, in fact infinitely many convex sets. And the idea is that intersections preserve convexity. So I'll note this here. So basically it means that if you have two convex sets, then their intersection is also convex. So by that argument, what you have here is an intersection of a lot of convex sets. So this whole thing is indeed convex, and this is the convex hull's definition. But this definition is somewhat not so mathematically useful, in the sense that you cannot derive a lot of structural property out of it. But there's also an alternate structural definition, more like an algebraic definition, that says that this set is same as this following. So what does this mean? Basically, it says that you pick a finite collection of points from your set S, and this collection can be arbitrary. And you look at the convex combination of this collection of points, right? And you do this for all possible values of k. That is, you pick any number of points, right? Any number of points from this set S. These AIs are picked from S, and you pick any lambda i's which are between 0 and 1 as long as they sum up to 1, and you take their convex combination, and you do this for all k belongs to natural numbers. So you will get a lot and lot of points, and the set of all such points will give you the convex set, convex hull of S. So basically, like intuitively, you can think of it this way. So earlier we had this set T, right, which was not convex. So what is this convex hull doing? So let me draw the set T again. This is my set T, and I want to find the convex hull of T. So in some sense, it will create this extension of the set. It will include these new points, right, apart from T. And then the claim is that all of this set here is actually convex. And you can now see that the problem pair that we had previously, right, x and y. Now, if you take a line like connecting them, then you will indeed see that it completely lies inside the convex hull of T. So indeed, this is a sort of convexification of the set T. So we'll call this convex hull of T. We had our original set T. And this is a very useful concept because a lot of times we will not be given a convex set, we'll be given some set, and then we want to convert it into a convex set and use the structure of convex geometry, the richness of convex geometry tools on this set. And if the convex hull, so the convex hull is the smallest such convex set. So in some sense, it's not too bad if you use the convex geometric tools on the convex hull to show some results, and those usually translate to the smaller set T, that is whose convex hull you took, right? So next, let me define the fundamental object that we will study, which is called the convex body. So we saw what a convex set is. Now a convex body is a restriction of the convex set. So convex body is basically defined as a compact convex set with a non-empty interior. We'll define what these terms are, and they will see why this is like a nice object to study. So here basically the first term, compact, means uh, basically this compact means that it's bounded, right? So bounded basically means that this set is contained inside a larger set, like larger open set. So basically think of this as like if we are in Rn, right? This Euclidean, n-dimensional Euclidean space. So in n-dimensional Euclidean space, bounded basically means that you can find a large ball of finite radius, right? So the large ball of finite radius, say we denote this as V of R, right? Vn of R. So basically this means that all x belongs to Rn such that norm of x is less than equals to R. So this is just a scaling of the unit ball. And so basically bounded says that you can find this R large enough, right? But still finite, such that your whole of this convex body is contained inside this ball of radius R. So this is bounded and closed. So closed basically means that this convex body, like if you take a sequence of points inside the convex body that converges to some limit, right? Then that limit point is also included in that convex body. So think of this in the sense that it's kind of saying that the surface of the convex body is also included in the convex body. So for example, if we have this say Vn, which I define as norm of x strictly less than 1, right? And now I take a sequence of points whose norm will converge to 1, then that limit point where the norm is actually 1 is not inside this set Bn overline, right? So it's not inside the set Bn overline. So this is not closed. So closed requires that you also have all limit points of the set included in that set. So these two definitions, so basically the compactness meaning bounded and closeness, these are equivalent statements. So if a set in n-dimensional Euclidean space is bounded and closed, then it's compact. And if it's compact, it's bounded and closed. And this is called the famous Hein-Borel theorem. But yeah, we'll not go into that. Now, the second part says that it's convex. So we know what convex is. The other important part is the non-empty interior part. Right? How do we define this? So what does this mean? Non-empty interior means that, like intuitively, it means that there is at least one point inside the set. So what does this mean? That there is one point around which, if you take an open ball, so what is an open ball? Think of an open ball as actually this Bn over bar. So call this Bn over bar epsilon. This is my open ball of radius epsilon, right? So I'll say that non-empty interior basically means there exists point P belongs to the set such that an open ball around P, how would that look? An open ball around P we will define as B over bar n P comma epsilon. That says that all points which are at a distance at most epsilon from P. And then note that the inequality is strict, right? This is a strict inequality. So we'll call this an open ball around P. I mention this. An open around P or centered at P. So we need that this open ball is actually a subset of is wholly contained inside the set. So call this convex body K, right? So let me use convex body K. Then you have there exists a point in K such that the open ball around this point is completely inside K. So these are the two basic uh, aspects of a convex body and how this is a subset of convex sets that we have seen. And yeah, now this convex body is what we will primarily focus on. So I'll now define certain operations on a convex body. So first we have this is a definition: symmetric convex body. So symmetric convex body here means that basically if you have a point x in the convex body, then the point minus x also lies in the convex body. So we will use, so hereafter we will use the notation k in most cases to denote a convex body. K is symmetric if near x belongs to k implies minus x belongs to k. So it's in some sense symmetric with respect to the origin, reflection at origin, right? So for example, if you have something like this thing, this is a symmetric convex body, but instead if you have something like uh, say something like this is not a symmetric convex body, because if you take the point here, right, and if you reflect it to origin, you get something here which is not inside the convex body. So no. Now second we have what we call a dilation of a convex body. So this basically means that we'll use some alpha in real, okay, and alpha k is the dilation such that alpha k is the collection of all points alpha x where x belongs to k. So basically think of this as a scaling operation. So if you have a say, ball, right, unit ball, and you take a dilation of size r, then you actually end up getting a ball of radius r. So this is kind of scaling up or scaling down according to the real number that you are given. But indeed, it is a scaling operation. And it can also have some sign changing operations also, because we allow alpha to lie in R. So alpha can be negative as well. So we can have an inversion with respect to the origin as well. Right. Then we have translation of a convex body. So translation basically means that you, for every point in that convex body, you just give it a fixed amount of offset. So again, take a vector b in Rn, then define translation as b plus k is equals to b plus x for all x belongs to k. So it's basically if you have a ball here and you're just shifting it by some uh, in some direction and length given by this vector d. Right. Next we have linear transformation. So linear transformation is basically like for a convex body. So you pick a t which is in our n cross n, and T is invertible, right? Basically, this is, you can think of this as a, so T is a map in some sense that takes vectors in Rn and maps it to some other space, right? So it can change the geometry of the object, or it can, basically you can think of, so note that if T is invertible, then there is like a bijection between the points, right? So the point x and point T times x, right? T is a matrix, x is a vector, so T times x is also a vector in size n. Uh, so x to T times x is actually uh, a map that is invertible, right? So we will use this idea of linear transformation to say that T of k is the linear transformation that is points T of x where x belongs to k, right? And we will see that this is a very useful notion, and in the following way. So we have this one final object called the ellipsoid, and we will study this object with respect to convex bodies. Like we will ask this question, that if you have a convex body and you look at all ellipsoids that are within this convex body, then what can you say about the ellipsoid with the maximum volume? We will see what maximum volume means and what this ellipsoid is about through John's theorem. So I'll define the ellipsoid. So it's basically ellipsoid E is given as B plus T times Bn. So we use the two previous definitions of translation and linear transformation. So first note that T times Bn, right? This is basically Bn is a convex body. T, okay, let me just write that B is in Rn and T is a positive definite matrix. So positive definite matrices are uh, basically matrices which have all eigenvalues positive, right? They are strictly greater than zero. And you pick a T. So this is, of course, positive definite matrix is a subset of R n cross n, and it's invertible. You can check that. So you pick such a T, and then T times Bn, the ball, the transform linear transformation of the ball using T gives you some other object, and you add, basically take a translation with respect to B, and you end up getting this body calligraphic E, and that is what we will call an ellipsoid, right? And this ellipsoid is basically a generalization of the 2D ellipse that we have seen. And so you can think of 2D ellipse looks something like this, right? And when you take this to high dimensions, this indeed becomes B plus T times Bn kind of a stuff. And the idea is that an ellipse is related to a circle in the following sense. So you have, say, a unit circle, right? And you skew it in some, like you rotate the circle, you first skew the circle and then rotate it in some direction. So you can think of this as circle, unit circle here. Then the first step, you make it inflated in one axis and deflated in the other. And then you rotate it, right? And then you shift it by some amount. So this way you can get arbitrary ellipses in 2D. And this is what we are doing in high dimensions as well. We are first using this matrix T, we are doing this step where we are changing the lengths along certain axes of this ball, like squeezing or elongating the ball in certain axes. Then T also incorporates this rotation, like how much you are rotating. And finally, adding B gives you this translation from the origin. So these are illustrations, and we will use this fundamentally to study uh, yeah, John's theorem and thereafter optimal design, right? And before ending this lecture, I would state two very fundamental theorems of convex geometry without their proofs, and you can find these proofs in like plenty of good resources on convex geometry. Like this convex analysis is a field of study itself, so there are very good resources, and you will find them in the lecture notes. So I'll state the first theorem, which is called Kara-Theodoris theorem. And this says that basically, if you have a point in the convex hull of a set A, right, then you can represent this point as a convex combination of at most n plus 1 points when we are dealing in n-dimensional Euclidean space. So it basically says that whatever is the dimension, you just need at most one more than that many points to represent a point in the convex hull of the given set. So formally, it says that there is a set given to you, subset of Rn, and you are also given a point that lies in the convex hull of A, which is also a subset of Rn, right? Then the theorem says that X can be written as I equals to 1 to n plus 1 lambda I ai, where ai belongs to A, lambda I belongs to 0, 1 for all I in n plus 1, right? And summation lambda I equals to 1. So it basically says that you just need at most n plus 1 points, right? And this lambda, so basically writing it this way, writing it here, basically you can allow certain lambda is to be 0. So indeed you can even have less number of AIs that you need to express X. But the power of this theorem is that it says that at most n plus 1 is sufficient. So this A might have infinite number of points in it, but you don't need at all those many points, right? If you are given a point in the convex hull of A, then there exists n plus 1 such points in A, at most n plus 1 such points in A, whose convex combination will give you this point that you are interested in. And this is a very powerful theorem, and it is used in many places to argue that you can actually get away with a very small number of points to represent the object of your interest, and you don't need a lot of things, even if your set is very large, right? This is a very beautiful theorem of convex geometry. And the next theorem that I'll state is, in some sense, the fundamental theorem of convex geometry or study of convexity, because it characterizes how convex bodies look in some sense and what is the basic geometry of these convex bodies. So it's called the separating hyperplane theorem. And as I said, like hyperplanes are very important objects in the study of convex geometry. So this theorem will tell you why. So this theorem says that you are given A, B to disjoint and non-empty subsets of Rn. Uh, Sorry, non-empty, disjoint, non-empty, convex subsets of Rn, right? Then there exists V belongs to Rn minus 0. So all vectors except the 0 vector. So there exists a vector in that set, and C belongs to R such that X inner product V is less than equals to C is less than equals to Y inner product V for all X belongs to A and Y belongs to B. So it basically says that you are given a set A, you are given a set B, both are convex, they are disjoint, so they do not have any overlap, and they are non-empty, right? Then you can find a hyperplane, right? So this hyperplane is nothing but here in this case is say, W belongs to Rn, W equals to C. So this hyperplane, right? This hyperplane will actually separate the two convex bodies. So you can see that X inner product V less than equals to C basically means that your A lies in the half space H minus and B lies in the half space H plus. So in that sense, this hyperplane H separates the two convex bodies, and hence like this characterizes how convex bodies actually look in some sense. So it's basically saying that if you have a convex set, then there is a hyperplane such that this convex body will lie on one side of the hyperplane. So basically you can think of it this way, that here you have a convex body and you have a convex body here, right? Then there is indeed a hyperplane that separates them. And in fact, this hyperplane does not have to be unique. There can exist many such hyperplanes, but there will exist at least one. This is what this theorem says. So this is a hyperplane. For example, this is also a separating hyperplane. And there can be many more you can see from this diagram. But essentially, whatever hyperplane you pick that separates them, then your set A lies on one side of this hyperplane while B lies on the other. That's the idea of the separating hyperplane theorem. And we will use this to prove John's theorem. And yeah, we'll see in the next video how that can be used. So yeah, thank you.